Okay, so now that we've covered pre-processing, I think we're ready to cover the training phase, which is the next step after pre-processing. So this is the learning phase or training phase. It goes by both names, and the idea of this section right here is to kind of learn a model, which is just basically we'll talk about the whole process in the next slides. But the idea is that that you want to feed different data sources to an algorithm in order to sort of derive the features of the data sources, and this is also known as a model. In such a way that okay. So the next step here is we're going to cover the training phase, also known as learning. And specifically, we're going to cover a graph neural network variant, which is called the GCN, which was initially proposed in 2017 by Kipf and Welling. Okay, so graph convolutional networks is actually a subset of graph neural networks. And graph neural networks itself is sort of a subset of neural networks in general. So first, we're going to cover what a neural network in general is, and then talk about how this sort of becomes graph neural networks, and then graph convolutional networks, just to kind of take that route. So first, let's go ahead and talk about generic neural network. So this is the core idea. This picture right here of a neural network or a deep learning sort of architecture, which sort of says, okay, we have a set of inputs, and we have a set of hidden layers, and then we have a set of outputs or predictions. And what this means is that so the input, we'll talk about the specific input to this use case, but the inputs is generally going to be an embedding or a sort of pre-processed representation of your data set. It can be a data set of images. It can be a data set of text. It can be a data set of graphs. But recall that we've already pre-processed these data sets, and we've represented as a vector of numbers, or we can also call this a tensor, or a matrix per se. So that's going to be the input to this neural network. Then we're going to have a set of pre-initialized sort of hidden layers. So we can choose to have this. This will depend on each use case. But like the most simple use case has one hidden layer. And for example, for graphs, it's common to have 2 or 3 hidden layers. And we'll talk about why in the next slide. But a hidden layer is, generally speaking, it's a tensor that's randomly initialized, or a value that's randomly initialized during the first sort of epoch. And we initialize these randomly because it's going to be so these hidden layers are also known as parameters, depending on the literature. You can also hear the name maybe weights, parameters, and yeah, I think that's coefficients. We can also call these, but they're the same thing. And this is going to be the value that we're going to be modifying as an iterative process. Depending on yeah, so as we sort of iterate over this neural network, we're going to be adjusting these hidden parameters or the weights in order to get a better prediction of our input. So yeah, I think this is pretty much it. The hidden value is it's just a value that's initially initialized at random, and it's going to be adjusted as we sort of iterate through the neural network or during the training phase. And the output is, in a broad sense, the prediction, the predictive capability of our hidden sort of weights, or our learned parameters, or our coefficients. every connection here that we see between inputs and hidden layers and output is usually a linear function, which means just recall the linear function is a multiplication between the first value, the second value, and you might sometimes have a bias. So in this case, we're going to be in this simple neural network, we would be multiplying whatever embedding or tensor input value by a random value right here. And then based on that, we'd probably apply like a softmax or something in order to generate an output, a prediction. So in this case, we're trying to predict between two categories or two values. This is also known as a binary classification, but you can also have like, I don't know, like 5 outputs, output labels in this last section. But it would generally represent like what we're trying to classify. Maybe if we feed a cat image as an input and we sort of run a forward pass, maybe our prediction is going to say that was that a cat or a dog? So whatever value is highest here is going to be our predicted value. Okay. So what is the input value for a graph convolutional network or a graph neural network per se? Our input is going to be a 2-dimensional matrix, which we already talked about earlier during our preprocessing. So recall that we were transforming this into the graph into a 2D matrix. This is also known as a 2D tensor. That would represent our input to this neural network. Okay, so how many hidden layers do we want to have? So usually the choice of hidden layers will depend on the implementation, but for the case of graphs, I think already mentioned that it's a good practice, or it's usually a common approach to have 2 or 3 hidden layers. So here we would have, for example, another hidden layer here and another one right here. And then hidden layers will also be linearly aggregated or linearly multiplied right here. Okay. So every connected layer here, depending if you have 3 hidden layers or 1 hidden layer, it's going to be a linear function between input hidden or hidden output or hidden softmax. We'll talk about this further down. Okay, so we know that the input is going to be an adjacency matrix, a 2D tensor. Why do we choose our hidden layers to be 2 or 3? So this basically comes down to kind of the graph structure. So let's say that we have chosen just a k. If we would have chosen a k equals 1 hidden layer, this is equivalent to let's say that here we have our red node, right? K equals 1 means that you're only going to get the 1-hop neighborhoods as shown here. So in this case, k equals 1 would be all the green ones. Now, if we wanted a k equals 2 layers, or if we were to have chosen 2 hidden layers, the graph representation for that would be, let's say, the red node would be represented as, let's say, the first hop and plus the second hop. So it would be represented as blue, red, blue, blue, red. So why are these colors? Let's take 2 hops. So k equals 1 hop, k equals 2 hops. So that's the blue layer right here. Now let's do the same example for, let's say, for this next node right here. So k equals 1 hop. That's this green node right here. K equals 2 hops. There is a blue and a blue. So those are these both of these blues, and we also have a the structure hops back to the original node because it's also a neighbor of the green node. So this is sort of already we're kind of saying, okay, that's k equals 2 hops. Now let's talk about the problem of having too many k hops or hidden layers, and why this might be like a necessary extra computation, so to speak. So here we didn't. It's not shown in this example in this picture, but I think the correct way of implementing this would also be that. So here we would have a red connection because it would hop back to the red, and then here we would also have a red connection. And notice how the red connection wants to is sort of starting to gather its neighboring structure based on how high the k is. That's all it means. How far away in the graph structure you want to explore, local to a particular node. But what happens if we go way too far down the line? Let's say we choose k equals 4 hops. So a 4 hop would be going up here. It would be 1. Or actually, let's go here, a simpler case, to CH3. So if we were to choose k equals 4, we would go to CH3, and then the next hop would go back here, and then the next hop would go back here, and then the next hop would go back here. Of course, actually, it might sort of exponentiate, and we would sort of exploring the same sort of structure that was already explored during the k equals 1 hop, right? So we're sort of repeating a lot of exploration in the graph, which is really not necessary. So here in this case, we'd be exploring at least twice. So let's say that we also chose k equals 4, right? We would also have gone here for the first hop, here for the second hop. For the third hop, we would have gone to these green nodes once again. And then for the fourth hop, we would have gone to the blue nodes. So just notice how it's just an inefficient way of, it's just extra compute. So that's why a good practice would be we're oscillating between the same sort of nodes. We're capturing the same information in many cases. So there's plenty of overlap the higher the k we go. So that's why it's a good choice to kind of choose a k equals 2 or maybe k equals 3 and not really go more than this. Of course, it'll also depend on the sort of how many the average edge degree of each node, but that's the general sense. Yeah, 2 or 3 hidden layers for graph neural networks is ideal choice. Okay, so we already talked about the linear function. A linear function is basically the weights or the coefficients or parameters, whatever we want to call it. It's the value that we're going to be adjusting multiplied by the input. That's the linear function that we talked about right here. How about the last layer of the neural network? So let's go back here. Let's talk about this last portion. So we've already talked about the input, the hidden layers. We didn't really touch upon a ReLU, but usually between each matrix multiplication, we would usually apply a ReLU function, which is also known as a nonlinearity. And these functions are just functions that help the process converge. It's just I don't think it's in the slides, but it's a simple it's as simple as for each coefficient, if you have a minus a negative sign, we would set that coefficient to 0. Yeah, just to help the process converge towards somewhere. Okay, so the last layer. Usually for the last layer, we want to generate a prediction, which so in this case we wanted to predict based on the input. We want to predict if the value is a cat or a dog, or maybe in the case of a graph. And we'll actually look at these examples during the next stage, which is prediction. We want to ideally kind of predict, okay, based on this input and multiplied by however many hidden layers we had, we at the end of the day, we're gonna either have we're gonna normalize these values, let's say in this case we have two values. So let's say that the first value were 25, and the second value were I don't know, something like 75. So ideally, we would want to normalize these values to sum between 0 and 1. So in this case, we would have 0.25 for this one and 0.75 for this one. And that's just kind of like a good practice for numerical stability. That's called as that's also known as a sort of softmax layer, where we in this case we're applying a softmax down to two nodes or two outputs, and here this is going to help us because in this case, if we have 0.75, then it's a higher probability that we're going to predict whatever value we've represented here. So this could be a cat or a dog, or let's say that this is cat and this is dog. This could also be yes or no. This can be toxic or not toxic. So in this case, if this value is higher than this value, then this is going to be our prediction value. And this is what is known as a forward pass. So notice that we've just we've just linearly aggregated, let's say, the input by the next layer, and then applied a sort of softmax, which is sort of a regularizer, down to the number of categories that we want to predict. In this case, a binary classification. So that's what this says here. So so we have our neural network. This is the last hidden layer, which is this hidden layer right here. Then we apply a softmax function, which is normalizing the values between 0 and 1, and that's just for numerical stability. So in this case, we have 4 categories that we want to predict. Maybe we want to predict here cat, dog, mouse, and horse, something like that, right? Four categories. And then we would apply cross-entropy loss. So cross-entropy loss is this is also known as the discrepancy between your predicted value and the actual value. So let's say that during the training phase, we have an input which is an image of a cat, and we know that we know because we have in our database we have a label for this particular image. We have a label that says that this image is equal to cat. But we're not going to let the neural network know that we know the result. This is something we're going to sort of keep for ourselves until the neural network generates a prediction, its own prediction. So let's say that the neural network generated its prediction, and it generated a prediction for a dog. Then we would sort of uncover like the real value, and we would say, nope, you were wrong. The real value was a cat. So that's also known as the loss function. It's just sort of the discrepancy between the predicted value and the real value. So in this case, for our use case, we have a data set of chemical a chemical data set, and we're trying to predict if a chemical is toxic or not. And we already have this historical information. This is already labeled data. So we would sort of run that forward pass, allow our neural network to predict if this is toxic or non-toxic. And then we would sort of do the big reveal here during the loss function, and we'd say, yes, you've predicted it correctly. Way to go. Or we would say, nope, you did not predict it correctly, and by how much, right? So that a common function for that to calculate the discrepancy between real and predicted value is cross-entropy loss, and it'll what this loss is going to do, it's just going to kind of calculate the difference between the predicted probability distribution and the real sort of value. So in this case, the real value right here could be I don't know, could be a 1, 0, 0, 0, because we know that the value was mouse. And let's say that our neural network said 0.25, 0.25, 0.25, and 0.5 right here. So we did predict it correctly, but the probability distribution will calculate a score for that. Okay, you're right, but by how much? Or wrong, but by how much? So it's just a discrepancy right there. Oh, okay, so yeah, we have the example right here. So So yeah, we have a chemical, we have our model, we have the target. So this is sort of like the known value, the one we hid beforehand, and the prediction. And based on this, we would kind of get a sense or a score of the loss. This is actually a better visual intuition here. And that's the forward pass. Okay, that forward pass is just matrix multiply and just try to generate the loss value at the end. Now we're ready to run the backward pass. This is a backward pass right here. So we're going to talk about what the backward pass is first. The backward pass is sort of in charge of adjusting. So recall that we talked about these hidden coefficients or parameters or weights is the value of the neural network that we want to adjust as an iterative process. So after we've calculated the discrepancy between real and predicted value, we're going to get a score. And that score we want to let's say that the score was 0.6 or I don't know, one. Let's just say a score, right, between 0 and 1. We want to sort of adjust these weights in a backward fashion, sort of as a feedback, or yeah, this is known as backprop. We're going to adjust these weights and get them ready for the next sort of forward pass. So in order to do this, usually we would a common question is, okay, yeah, I know I was wrong. I know by how much I was wrong, but by how much should we adjust these weights right here? Should I adjust this by a magnitude of 100x per se, or should I adjust it by like plus 100x or minus 1x? Like by how much do I want to adjust? Because and we do not want this to be a random process, so that during each sort of epoch, we're actually getting a better accuracy each time. So that's where the atom optimizer comes in, or optimizers in general. So optimizers. An optimizer is sort of it's an algorithm that's going to help us determine, okay, by how much should we adjust those weights, and it's an adaptive process. So maybe it'll during each epoch or each neural network loop, it's going to probably modify the value that we want to. This is also known as the learning rate. So by how much we want to adjust those weights. Notice here that, let's say during the first epoch, it's going to sort of provide a larger value because we still don't know by how much we want to adjust the weight. All we want to know is that we want to get closer to having a super small loss score at the end. That means that our predictive capability is pretty high. So maybe the next epoch we might we might get further confidence that we're sort of that our coefficients are predicting an accurate sort of model. Then maybe the next epoch, ideally we would start adjusting our learning rate by a smaller magnitude during each epoch. Which means that our accuracy is getting closer to our target, and that's what an optimizer does. So for each epoch, it'll just determine a learning rate, which is again by how much we want to adjust our parameters. Yeah, during the backward sort of process. This is going to help with convergence of our model again to actually allow the accuracy of our model to kind of increase instead of just randomly fluctuating between 0 and 1, right? So we do actually want to learn something that's closer to our target, our predictive capability. So that's also known as learning sort of process. So there are many different optimizer algorithms, but a common sort of optimizer to use is known as the atom optimizer. And there are different optimizers here, but that's sort of out of the scope. There are some modern, yeah, depending on the architecture and your on each use case, you might want to leverage a different optimizer. And there are some, I guess, some recent sort of optimization strategies as well. But as a, I guess, generic rule of thumb, or that the industry has adopted as a best practice, so to speak. Of course, if it's compatible with numerically, we'd just go for Atom. It's a popular optimizer that works well in practice. Okay. So we talked about our already forward pass, the loss. Our Atom optimizer is going to tell us, okay, by how much our learning rate, by how much we want to adjust these weights, by how much magnitude during this backward sort of propagation. And this is actually a derivative sort of. So this loss value right here, I'm not going to get too much into it, but it's called also the back gradient, sort of taking the gradients in a backward fashion, backward in time per se. But yeah, that's a more the detailed version of it. And yeah, during our next phase, we would actually want to run again a forward pass, and it's likely that since we've already adjusted our weights, and they're not random anymore, they're actually sort of converging toward a correct prediction. During the next forward pass and prediction, we would have a better score or a better accuracy of our predictive capability. Okay, so at the end of the day, the model that we're learning is going to be these hidden weights. Yeah, a model is just basically whatever at the end of many iterations. It can be, I don't know, as an example, 100 or 1,000, 10,000 iterations, depending on the use case again. After all of those iterations, which can get computationally expensive, since you're actually iterating over each item of a data set, and not only, let's say, one particular item. Let's say that our data set is 100,000. In our case, we have 110 million chemical data sets. So this is actually a computationally expensive process, the learning process. Yeah. So after you've learned sort of the prediction capability, a model, you'd ideally want to persist these or save these weights, just so that, I don't know, and in the future, if you want to generate a prediction, you can just load these weights, which have been already adjusted during the learning phase, and just run a forward pass and that would mean a prediction. Anyhow, so let's talk a little bit about epochs. So an epoch is a forward pass and a backward pass through all the data set. That's it. So an epoch is a forward pass. Remember, we predicted the loss here. We've adjusted our parameters and based on the gradient propagation, and we did this for just one data point, one image per se. But doing that for all of your data set is also known as an epoch. And you can choose to do it in many batches. So like in our use case, we chose to parallelize so we also containerized our yeah, I'll talk about the architecture further down, but you can choose to, let's say, parallelize your implementation, and you can say, okay, each parallel executor, in this case, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So each process or each containerized process or learner, I don't know what the correct term is, can process, let's say, 100, a subset of the data set, and each of these parallel processes can process 100, and that would actually reduce our training phase to like we would be able to train 10x faster, provided that we have the enough sort of hardware and hardware partitioning. So yeah, right now, this is a little off topic or side note. right now, for example, CPUs are super useful for partitioning the CPU, the cores. You can leverage like half a CPU, or sorry, half a core, or even a fourth of a core, or I don't know. It goes down to the millet core, for CPU processing. But the problem, or a problem right now for GPU, GPU is pretty cool because it processes very, very fast, but you cannot sort of partition these devices yet as much. I think right now, or the latest I've heard, is that you can partition these devices into seven cores, so to speak, or seven. A GPU, you can partition it into seven sub pieces. So you can parallelly process. You could have 7 containers, each with their sort of share of GPU processing in parallel. And I'm guessing that as the industry evolves, it'll become more parallelizable. But that's actually pretty cool for distributed systems. Since we're talking distributed systems here, that's kind of like the ideal case. Okay, sorry for taking too many tangents on this topic, and I know we've talked about this too like a long time, but I just to finalize, what is a model? So a model is just going to be the trained the tensor weights. So here, recall that we're adjusting these weights, and they're all actually a tensor. So we're adjusting these weights iteratively. Maybe we're going to have 100 cycles here, or loops, sorry. 100 loops for each data set. So ideally, we want to sort of persist this to disk, whatever our last learned representation is, or our last weights, and that's the model, so to speak, the final weights. So we'll save this model to a disk after the training, and hopefully, I guess, for example, let me show the architecture. Okay, an architect. So after we've saved this model to disk, or even like a database, it doesn't matter. We could run inference tasks quite quickly, because we'd just load the model to memory and process, let's say, new chemistry, and determine if it's toxic or not. And we could also say, okay, our model predicts toxicity with a 95% degree accuracy. So and this would be a fairly fast implementation. So that's why we want to save these models to disk, and in order to load them for future prediction tasks. Okay. So the distributed phase, maybe we'll cover this in the demo of how we would parallelize our processes, and then how we're gonna sort of reaggregate reaggregate the model. So just a quick sort of what do you call this in a quick sort of spoiler alert, or yeah. We're going to use a MapReduce framework to kind of for this sort of parallel training processing framework. But yeah, we'll cover this in the demo.